in this video. Hello everybody, and welcome to the 74th video of the channel. As you see, it is actually a different thing. It's called Intro to Calculus. The reason I actually changed the series and I actually stopped mid-series is because it gets quite boring researching proof after proof and theorem after theorem. And also I feel like it's also going to be boring for you if you see me ramble on about theorems for a pretty long time. So I decided to do an Intro to Calculus video to explain the very core concepts of calculus before we go back in and jump back in to advanced trigonometry and geometry. So, thank you so much for listening to me. Please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And if you have any other suggestions, please make sure to go down in the comment section below and comment whatever you need to comment so I can make this channel better for you and for everyone else who's watching. So, without further ado, let's move on to the lesson. Today's lesson is about an introduction to the two main branches of calculus. These two branches are called differential calculus and integral calculus. Now, differential calculus and integral calculus, as I said, are the two main parts. Now, and they're pretty self-explanatory. So, differential calculus focuses on derivatives, and integral calculus focuses on integrals. So, these two are pretty much two almost opposite operations, kind of like adding or subtracting or multiplication and division, which show that these two are different, which show like the exact opposite meaning, but they actually kind of have different but almost similar uses in many problems. Calculus, as a total, is used in many things, including finance, applied mathematics, physics, engineering, and pure mathematics, with higher fields being like linear algebra and differential equations. So, today I'm just going to look a bit at differential calculus and a bit at integral calculus and not explain that much. Next video, I will most likely do a little bit more of an in-detail depth, or I might even explain limits to you guys. So, let's start with differential calculus. Differential calculus is the calculus that involves derivatives. Now, the basic form of the derivative is dy over dx, which basically means the derivative of function y with respect to function x. So, what that means is if I have the derivative of x squared, so d of x squared instead of y over dx, it's not dividing and simplifying like algebra. You're like, oh, okay, so the d's cancel out, then this cancels out, so then this becomes x. Nope, in fact, that's entirely incorrect. This is different. This d of x squared over dx is an entirely different operation. Now, geometrically, you represent derivatives by the instantaneous slope at a certain point. Now you might be, what's that? So, let's say we have a function like x squared, which is not exactly a slope. Which is not exactly a linear function, so you can't really figure out its slope. So, the graph of x squared would probably look something like this. So, this is probably how the graph of x squared looks. And as you realize, it doesn't have a constant slope. So, if we say the derivative at a certain point, let's say x is equal to 2, we mean if we draw a tangent line, what would be the slope of that tangent line? In this case, it's 4. Now, the general form of the derivative is, let's say I took the instantaneous slope across all the points in x squared. What would the formula be for that? So, in that case, it would be the derivative of x squared over dx is equal to 2x. So, and as you can see, if we plug in 2, that means the derivative of x squared at point 2 is 4. So, now that's about it for differentiation, which is like the basics of differentiation. Now, of course, there's more types of differentiation, like implicit differentiation. There's different rules, like the power rule, the chain rule, and there's even differentiating a function multiple times over. So, now let's get into integral calculus. Integral calculus is the other half of calculus. Now, instead of finding the instantaneous slope, let's use x squared and geometrically define integral calculus. So, let's first draw the graph of x squared. This is the graph of x squared. Now, let's say I wanted to do this. All right, I want to find the area from x is equal to 0 to x is equal to 2. So, as you can see, this is not any geometric shape. But let's say we zoom in, you might be able to tell that we could maybe use rectangles. So, if we have many rectangles, here's a rectangle, and then here's a rectangle, then here's a rectangle, then here's a rectangle, then here's a here's a rectangle, and then here's the final rectangle. So, if we do the area between 0 and 2 with these rectangles, we'll get pretty close. And the more rectangles we add, so let's say we have each rectangle be half the width, we'll get more and more accurate. Now, I'll talk about this later in my series of Introduction to Calculus, but there's a specific formula, and this is called the Riemann sum of the function. So the Riemann sum, or like the area under the curve, is used by having a certain amount of rectangles with a certain width in a certain interval. I know that's a lot of certains. So to figure out an approximate area. Now, what would happen if we have those rectangles equal to infinity and have the heights of them perfectly match the height of x squared? So we can basically just color in this graph. Now, as you can see, since we have the full graph colored, you will get a perfect area. Now, this is called the definite integral. Now, the definite integral is represented with this weird S-like symbol, the lower limit, which in this case would be 0, and the higher limit, which in this case would be 2. So, then we have the function x squared followed by dx. Now, how much area is exactly in there? It is actually 8 over 3. So, the integral of x squared from 0 to 2 is equal to 8 over 3. Now, the general form of the integral is, what would happen is if we have all those areas and we wanted to figure out a formula, that would be x over 3. X cubed over 3. Now, since we have x cubed over 3, we actually have to add a constant c, because in derivatives, all constants become 0 when you're taking the derivative of something, because the slope doesn't really depend whether you're shifting the entire graph vertically or horizontally. So, what happens after that is we have to add back that c, because integration is the exact opposite of differentiation. So I think that's about it. Thank you so much. See you in the next one. And bye-bye. And I really hope you enjoy watching this video. I think it's a change from the usual old advanced trigonometry and geometry. So I'll see you in the next one. Bye-bye.